So far, we have looked at how to make a new surface by depositing a new layer on. And now we will look at actually chemically bonding a new surface to an object, with grafting, self-assembled monolayers, and plasma methods. We will start with grafting. Grafting is a method of surface functionalization which is generally used for polymers. Polymers are very useful synthetic materials as they can be designed and manufactured for the desired mechanical properties. However, often the polymer which is mechanically right may not have the right surface or functional groups on the surface which are needed for the application. Grafting is the concept of joining two or more polymers, such that we have the first polymer as a linear backbone, with the second grafted polymer coming off as side chains. This approach can enable you to keep the original polymer's mechanical properties, with its surface coated by the grafted polymer, which contains the functional groups required for the application. There are two types of polymer grafting for surface functionalization: grafting to and grafting from. Grafting to is covalent immobilization of a pre-made polymer onto the substrate. This means there needs to be functional groups on the surface of the substrate, which the head groups of the graft polymer can react with. Grafting from is a different approach, which involves initiators on the surface of the substrate being used to carry out polymerization in situ. This means that the monomers for the graft polymer will add one by one to the substrate so that polymerization takes place at the same time as grafting to the surface. In general, as the grafting to method involves attaching pre-made polymers to a surface, the polymer in solution assumes a random conformation as a result of entropy, so the grafting density is low due to the steric repulsion between polymer chains being added. Also, incomplete coverage and non-uniform coating of the surface can be a problem. However, in grafting from techniques, as they involve in situ polymerization of the second polymer onto the surface, the grafting density is much higher because the polymers can be built up in a straight chain conformation. Also, surface coverage can be more uniformly spread and thicker. Grafting a new polymer onto the surface can be difficult if you do not already have functional groups on the surface which the new polymer chains can react with. If, however, you can generate a reactive species, such as an ion or a radical on the polymer backbone, this is reactive enough to attack an atom or molecule, form a chemical bond with it, and thus pass on its reactivity. This new molecule can then go on and attack another molecule, and hence the reaction is propagated and polymerization occurs. There are many ways to make that first reactive species and hence initiate the reaction. For example, using high energy sources like ultraviolet light or gamma rays, or by chemical reactions. Now we will look at self-assembled monolayers. Self-assembled monolayers are highly organized, regular arrays of molecules which arrange onto a substrate to form a new surface. They form by spontaneous chemisorption and organization onto the material as a result of the head group of the long molecule having a high affinity for the substrate. A common example of self-assembled monolayers is the chemisorption of long-chain alkane thiols onto gold. The gold metallic surface forms a very strong chemical bond with a hydrophilic head group, which in this case is a sulfur atom. The sulfur is connected to a long tail group, which is an alkyl chain and stretches straight out. The chains orientate far from the substrate such that the other ends of the organic chains form a regular and close-packed new organic surface. An emerging application of self-assembled monolayers is in micro-contact printing, also known as soft lithography. This is a method of replicating or producing structures with specific surface features, some as small as a few micrometers across, using a stamp, similar to how stationary stamps are used in the office. As the alkane thiols stand in a straight, ordered fashion on the gold surface, if they are applied onto a stamp first, and it is pushed against the gold surface, the alkane thiols will adsorb to exactly where they are placed. This is a method for using one stamp to produce many very specific surface patterns which are all exact replicas of each other. There are many applications for this chemistry, such as in biosensors. We will now look at plasma functionalization. Plasma is often known as the fourth state of matter, as it cannot be characterized by the traditional three states of matter of solids, liquids, and gases. It is made up of a diverse mixture of electrons and nuclei, ionized particles, radicals, and neutrals. It sounds uncommon, but it actually makes up the majority of the universe, as plasma makes up many atmospheres of stars, including our own sun. At the extremely high temperatures of thousands of degrees centigrade or more, the electrostatic forces binding protons, neutrons, and electrons are overcome. Plasma can be used to functionalize surfaces, deposit polymers onto surfaces via plasma polymerization, or be used as the initiator in grafting. Plasma is an incredibly useful method for making a surface, and it comes with so many benefits over other methods. To name just a few, plasma is a low energy method because it can actually be used at room temperature. It also uses no solvents and has no waste. The treatment is fast and can be done on pretty much any material or object, opening it up to a huge variation of applications. Also, the treatment is conformal, which means all the surfaces throughout the porosity of the object can be functionalized, not just the very outer visible layer where the light hits it, as in grafting. Plasma is able to chemically bond many different molecules onto the object, leading to many new properties which can be added, such as water repellency, oil repellency, and many others. In the next tutorial, we will learn how it is that plasma can be used effectively in the lab, and how it can make new surfaces. The benefits and the potential applications of plasma surface functionalization are so widespread, making it a huge and exciting topic in the world of chemistry. In summary, we have taken a look at many different ways of making a surface. That could either be from depositing a new surface on, such as in painting, powder coating, spin coating, laser cladding, or electroplating, or from chemically bonding a new layer onto the substrate, such as in grafting, self-assembled monolayers, or using plasma. The areas of research within surface functionalization are constantly ongoing, with new applications being developed every day.